I mean, it's not fair, but I want you to kind of stay with me on this. So you'll have this document soon. Here's the whole point of statistics. You want to know something about a population. Usually it's average. But you can't. That's the sucky part. You can't have its average. So what's the best you can do? As Jada and Elena pointed out before, the best you can do is? Predict based off of what? Yes?
On your formula?
Before you use a formula, what do you have to do? You got to draw a sample and get some data to use, right? You got to draw a sample and get some data to use. So you're going to draw a sample. We're going to call it size n. Just in general, size n. N equals 100, n equals 300, n equals 1,000, whatever. And that's the best you can do. That sample is going to have an average, which we call x bar. You guys immediately figured out that if we draw many, many samples from that population, the highest bar of what's called the sampling distribution, which is what those bell curves we looked at were, are going to be bell-shaped. Yay. That's a yay. Because if it's bell-shaped, that means we have tools. Is anybody else blown away by the fact that those curves, the population curves, were so wonky, but all of your sampling distributions were beautiful bells? It's kind of early in the morning. Maybe it's a little bit early to kind of deal with that, but I'm blown away every time. Every time, because I get different curves every term. But they're essentially the same curve, aren't they? They're essentially the same curve. It's wild. It blows my mind. I'm also heavily caffeinated, which helps. But nonetheless. So, and double yay, we get to center it on mu. Now, this is a little bit symbolic. I made up a symbol. I called x double bar. And the reason I called it that is, I first calculated all the sample averages and then averaged the sample averages. So I made up a new term. Hope that's okay. X double bar. And friends, this is rare in a statistics class. That equals mu. That's not squiggly equals. That's equals. In case you want to see why it's exactly equals, I have a little proof on the enrichment page of the website. It's all written out algebraically. If algebra makes you break out in time, just don't read it. But just, this is true. This is true, as n goes off to infinity. Fair? Okay. Now here's the problem. I thought the last slide said x double bar equals mu. And it did. What does this say? X single bar, which is your sample average, doesn't equal mu.
So what was the double bar again?
That's the average of all the averages, Haley.
Oh, okay.
So, now, that's a symbolic explanation of what you guys said verbally very nicely. When you looked at these sampling distributions, you said, oh look, the highest bar is mu. Yes, the highest bar is mu. The highest bar contains mu, I should say. However, there are other bars that don't, but the ones that underestimate mu cancel the ones that overestimate mu, and on average, they target. But remember, that's an average, not a guarantee. So Haley, does that make sense? That's a very wonderful question you just asked. That's why this second statement here is true. On average, your sample means target mu, but the individual sample means are not exactly equal to mu. This is the problem I have with mass media, this step right here. They will do a study in which 16% of the sample has a certain characteristic, like, I don't know, color blindness, or potassium allergy. We'll make up something. Potassium allergy. 1 in 6 Americans has a potassium allergy. No, 1 in 6 of your sample has a potassium allergy. That is not the same as 1 in 6 Americans. 1 in 6 in your sample is not the same as 1 in 6 Americans. You see it all the time, Jada? Yes, and it's frustrating statistically because that's not true. They're off by what's called a margin of error. Right. And that's what we're getting to right now, to control for that. So, that's what this guy is. Now here's a new term-ish. New term-ish. Okay? You noticed that your sample standard deviation starts to shrink. You noticed that right away. The bells, as JD said, the bells are getting shorter, and Elena said they're getting taller because they have to make room for the shortness. The area has to go somewhere. And what's totally rad is that sample standard deviation, which FYI is often called the standard error. Now let me see if I can draw a distinction between those two things. Mathematically, they indicate the same thing. It's a plus or minus around average, mathematically. Plus or minus around the average. The reason I believe that this has a different name is twofold. Number one, this is its formula, if you will. You get it by taking the population standard deviation and dividing it by the square root of the sample size. This is the part you guys just figured out. Remember how I said 64? You're like, 1/8. 49, 1/7. 10,000, one. I said the 1/100. You said the 1/1 or whatever you said. It was an awesome new word. I love that. So you guys figured this out. But the problem with this, too, the problem with this I have is you have to know sigma. But you don't have to know sigma. You can generate it from your sample. The reason I think I like this reason better, rather than a mathematical formula reason, the reason it's called standard error is because we are going to use this inferentially and not descriptively. In other words, if you take a sample and you tell me S, which is the sample standard deviation, that only holds for that sample. You can't blow it out to do anything else in your population. Standard error, although it's the same idea, allows you to form a margin of error and then make predictions. So your article shouldn't say 16% of people, 1 in 6 Americans, have a banana allergy. It should say 16% plus or minus 4%, which would be as little as 12% or as much as 20% have a potassium allergy. You see what I'm getting at? See the difference there? The difference, we'll get to in a second, why we care about the plus or minus. But this is the beginning of the plus or minus. The standard error is what you're going to add and subtract from your X bar to generate what's called this confidence interval. We'll get to that momentarily. Just bear with me. Is this okay as far as, are you seeing the connection between this and what you guys just inherently kind of gut checked, figured out in Excel? Yeah, don't memorize this, please. Don't memorize this. It's a formula, but don't memorize it. I mean, it'll be, if you need it, I'll put it on the board. You probably won't need it though. This is going to be a little bit vomit-inducing. But you know this already. Read that. Read that, friends. Tell me what it means.
X plus or minus.
Jenny, help me. Help me. Help me, friend.
The plus or minus the 2 standard deviations.
It's the same thing we've talked about for weeks. It's the plus or minus 2 standard deviation. I'm gonna muck up the blue curve over here. I apologize to my blue group. Here's this is beautiful sampling distribution, right? What you're seeing 95% of the time is an average standard deviation, or excuse me, an average, sample average, plus or minus 2 standard deviations. But those standard deviations are constructed, they're called standard errors. So when you go out 1, X bar plus, whoops, that's too far. X bar plus the standard error. And this guy right here is X bar minus the standard error. That's going to trap about 68% of your sample averages, isn't it? 1 standard deviation, or 1 standard error. If you go up to 2 of them, you're going to trap about 95% of them, right? X bar plus 2 standard error. And this guy down here, X bar minus 2 standard error. So Jenny, right away, recognize those 2 symbols. Right away, recognize those 2 symbols. What is this guy in the middle? What is this mu in the middle? Yes, that is your population average. Do you know where it is?
Yeah, it's going to be in the middle.
It's got to be between it, say 95% of the time.
Yep.
Right? 95% of the time, what you're looking for is between these 2 numerical values. And that's why it's so important to say things like, Mr. Pocket, that's why it's so important to say, not that 1 in 6 Americans have a banana allergy, but that between 12 and 20 have a banana allergy. Now you've allowed for all that error. And when I say error, I don't mean bad error, I mean measurement error. Your sample is not the same as the population as you saw in Excel. Press an F9, it's dancing around. But you've got 95% within those 2 standard errors. Fair enough? Yeah? Now, sometimes you're out. Sometimes you pop out. Those are called outliers. We'll deal with those in 244. I promise you that. Lady, go ahead. You had a question.
No, it's not a question. I'm just like trying to figure out again X double bars. And it can be explained. Do you remember you told us that within this,
yes,
it's also bell-shaped?
Oh, for sure.
So
For sure.
That's what the thing. It's just like
And
more
this
accurate.
brings up that word, accurate. I've heard you guys use 2 words today. Accurate, and I heard somebody say precise earlier. Here's the problem. We have to make sure we understand this. Here's the next step. Standard error, make sure you got this word, inversely proportional to the sample size. What does that mean, inversely proportional? Inverse is reciprocal. Inverse proportion means as one goes up, the other goes down. That's inverse proportion.
With the same, in the same number. Like
It's square root of the sample size. Square root. It's a multiplier square root of n. So as the sample size goes up, the standard error goes down. Now read this next sentence. As the sample gets larger, the precision gets better. Yay to the 4th. Now, I want to make sure You guys understand the difference between accuracy and precision. So, what I've got here are 4 targets. In one of those targets, assume that we're aiming for the middle. Let's just assume we're aiming for the middle of the target, okay? In one of those targets, we have precision and we have accuracy. In one of the targets, we have accuracy but low precision. In one of them, we have high precision, low accuracy. And in one of them, we've got neither precision nor accuracy. Somebody grab one of the 4 and tell me which is which. There's 4 potentials. Grab one of them. David, go ahead, grab one and tell me what it is.
Upper right would be precision without accuracy.
Everybody got that?
Yep.
Up here, we have high precision. Precision means not much variance. So tightly clustered, however, we've missed the target. Accurate-wise. Fair enough?
The
Elena?
last one has both.
This is both, is it not? High precision and high accuracy. Because we hit the target, and we hit it often with very little deviation. What's this guy? That's neither, isn't it? Because oh, excuse me,
No,
that's neither.
No,
That's neither.
that's
This
one
is
of them.
accuracy,
Yeah, but no.
but low
Yeah,
precision.
because
Because we're actually centered on the target, we're very wide around the target. That right there
Nothing.
is lack of accuracy and lack of precision. Now here's the good news. With the central limit theorem, you never have to worry about those 2 situations. Because what are you guaranteed with the central limit theorem that we're studying
You
about
will
right now?
hit
You are guaranteed on average you're hitting the center of the target. That's what the bell curves give us. On average, you're hitting the center of the target. What you're not guaranteed is amount of precision.
this one.
So, in other words, I said earlier, between 12 and 20% of Americans have a banana allergy. 12 and 20%. What would this interval look more like?
Margin of error.
Right? So make up some other percentages that would be more readily represented by here. Okay, Jen. So this is 12 to 20. No, okay, I'm sorry. I see movement. I assume it's going to be an answer. So 12 and 20, make up one over here. What would this be like?
8.
Oh, that would be less
Oh,
precision.
no. Okay.
Right?
Sorry. Then,
So we want to go maybe, well, 16 is the actual average. So how about 15 to 17? How about that?
Yeah.
So if the center is actually 16 of your sample, and you go 12 to 20, that's 4 up and 4 down. So more precision would be less up and less down. Same center, right? Same center.
14, 8.
14 to 18 would be a great example. 2 up and 2 down versus 4 up and 4 down. Here's a question. In order to get that level of precision, this is a tricky question, what will we have to do to our sample size to go from a margin of error of 4 to a margin of error of 2? What would you have to do to your sample size? You have to go up.
Double it.
More than double. It's a function of the square root, remember. You'd have to, this is a totally bastard question, it's an algebra question.
Square power.
You'd have to quadruple it, right? Because the square root of 4 is 2. So to cut it by half, you'd have to actually that was a bastard question, I apologize. You guys made me think of it when you said 14 to 18. We'll revisit that in 244, I promise. Maybe we won't. I saw some drag use on that one. Fair enough?
Yeah.
So, friends, we are guaranteed accuracy with the CLT, but our precision only gets better as our sample size gets larger. So if our sample size got larger here, what would happen to these dots?
They group more.
Yep, and eventually they'd be so grouped down that they would look like one dot. But then we could go into that one dot and pull it apart and look at it more microscopically, and it would spread back out again asymptotically. Bell within the bar. Whew. Now, this is the last bit. You'll notice that you didn't have to get very, very large samples in order for that bell to kick in. You saw it with 4. A sample size of 4, and the bell's kicked in. There is a number out there, 30. I don't know where this number comes from. Every textbook talks about it. It's accepted. As you just saw, we got great results with 4. We're going to get awesome results in 244, estimating oil spill flow. I mentioned the BP Deepwater Horizon explosion a couple of weeks ago with you guys. We're going to estimate how much oil came out of that with 6 data points. 6. Nowhere near 30. 6. We get good results. I don't know where 30 comes from, but I can tell you this. As your sample gets larger, the more precise your result's going to get, and the better. As long as your data is good. If your data is garbage, you're just going to have more garbage data. And you're going to get results that don't make any sense. But as long as your data is good, the more the better. And you're going to get more precision. You're guaranteed accuracy, you're going to get more precision. So for some reason, I don't know why 30 is used, but it is. It's one of those accepted values in statistics. Go ahead, Elena.
Probably just from 30, they started thinking about like,
I don't know if it's, honestly, I can't track it down.
yeah.
This is one of those, there's like a half a dozen statistical questions, because I'm not a trained statistician. I've been trying to track down these numbers for years. The only thing I've gotten close to is, there's a thing called the t-distribution, which is like the z-distribution that we've been talking about, the standard, it's the normal curve. Once you get around 30, the t and the z start looking the same. And maybe that's it, I don't really know. I don't have a good answer for 30. The question is, or the thing to remember is, as soon as you start sampling, the bell curves kick in. Even with a sample size of 2, that's insane. That's insane. Now, of course, the problem will always be this. Oh no, I can't look at this, I have to look at what you guys put. The problem will always be this. This is a sampling distribution. These are all sampling distributions, which means you have one of the averages in this distribution. So you might be, friends, you might be the one that was in here from 6 to 7.
Yeah.
Which means you're nowhere near the average, are you? You're nowhere near the average. The average is over here. So that's why we put what on your sample average? What do we do? Jenny, you nailed it earlier. You put a plus or minus 2 standard error on there. And then the idea is that you've got a wide enough interval to actually capture the average. You see what I'm saying? So when you say it's between, say, 3.5 and 7.5, you're not guaranteeing where it is, except between those two values.
At least you'll hit it.
It's still in there somewhere. Now, sometimes you're going to miss it, aren't you? If you were the sample average out here, and you put a plus or minus 2 SE on there, you're going to miss it. But that's why, when I think it was Haley, you said it's going to be in that interval, and what did I follow that with? You said if mu's going to be in that interval, and I followed with,
Maybe.
I don't remember.
I said better than maybe. Maybe sounds too 50-50. Oh, it's not 50-50, it's 95-5, right? I said I'm 95% sure it's in the interval. And I'm picking on you, Kelly. I think it was you that said it. It was either you or Jenny, one of you two. But in 95% of the time, it's going to be contained in an interval. You're going to miss it 5% of the time. Those are called the outliers. But then again, aren't these outliers? Those are very rare events. They shouldn't have happened. They shouldn't have happened, which means you got slightly deviant data, which we'll deal with. Total type 1 error, we'll deal with that in 244. As long as you adjust for the errors. Suppose you want less error. You want less error? So you want this curve to get rid of this tail over here? What should you do?
Chop it.
Chop it how? Legally, statistically. Can't just ignore it. Go to the study again, but do what, Haley? More samples. Want more samples? Make these guys go away?
Well, because like you said, because the more it goes, more it comes
And you're saying the correct thing, Haley's perfect.
Yeah.
All I'm saying is you can't just ignore that tail,
Right.
but you can make it go away. Increase your sample size.
So essentially,
Essentially, you're chopping. But that's why I'm saying doing it legally
Yeah.
means increasing the sample size.
Eventually.
yeah.
Fair?
Yeah.
Beautiful. Love it. Making sense?
Yep.
My friends, that is Math 243. That is it. That's the course. No, it's not. We have Math 244. Yeah. Some of you anyway.
Yeah.
Who's taking 244? A couple of you? Only a couple of you. Good. We'll catch you. Maybe you usually have Donna or the other. But it's great. It's a logical extension you'll see immediately.